Magnetic dipole moment of a current loop. I have a current loop here. That means a conductor carrying a current. This is a current loop. And area enclosed by this loop is A. And the current carried is I. Then if you take a product of current and area, that is equal to the magnetic dipole moment. So magnetic dipole moment is just a product of current and area vector, the area enclosed by the loop, that is called as magnetic dipole moment. And where is dipole here? The name itself says here di. Di means two poles. Is there any such north pole and south pole here? No, we are not observing any such poles. But in reality, if you consider two circular loops, I will recommend you to watch the previous videos where I explained about the circular current carrying loop, the nature of the magnetic field. There I explained it, and it is just again revision of that. Suppose I have two conductors, circular conductor. In one conductor, the current is in clockwise direction, and for the observer, the phase appears like or behaves like a south pole. And in another conductor, if the current is flowing in anti-clockwise direction, for the observer, it appears like a north pole. It behaves as a north pole for them. But here there are two coils we considered separately. But here you observe it, and there are two observers for the one coil, and one observer is here and one more observer is standing here, and the coil is between them, and the coil is like this, and for this person the current is in anti-clockwise direction. So current is in anti-clockwise direction, then for this person it appears like it is north pole. And for this particular person standing, for this person it appears like the current is flowing in clockwise direction. Then for him the phase of the coil looks like a south pole. So two poles exist in a single current carrying loop. That is why it is called as a dipole. Suppose if there are n number of turns in it, not only single turn, there are n number of turns in it, then the magnetic dipole moment M is equal to NIA, and its SI unit is ampere meter square. Next topic is here the current loop as a magnetic dipole. Here we just told it in this particular topic, we just told the magnetic dipole and the definition of magnetic dipole. It is just a product of current and the area vector. But here, is it a magnetic dipole or not? Let us check it. So magnetic dipole is just a bar magnet also you can consider. If there is a bar magnet, it consisting of two poles separated by certain distance 2L we can consider. So north pole and south pole separated by a small distance. This is called as magnetic dipole only. But current loop as a magnetic dipole. Here, this is the heading. Now I have a coil. I will consider a coil carrying a current in it. And we studied in derivation that wherever the current is flowing through a conductor, circular conductor, it produces the magnetic field along its axis. And magnetic field at point P along the axis is given by B is equal to mu naught Ni A square divided by 2 times x square plus A square to the power 3 by 2. where A is the radius of the circular coil and x is the distance where we are finding the magnetic field from the center O of the coil, and n is the number of turns in it. Suppose, I will call this as equation 1. Suppose if x is very greater than A, this x is very greater than A, we can drop A square term in the denominator. We can drop A square term in the denominator. Now, how the equation appears like B is equal to mu naught n I A square divided by 2 times x square. A is dropped, that means A value considered as 0, x square to the power 3 by 2. So simplify this, you are going to get mu naught n I A square divided by this 2 and 2 will be cancelled. You are going to get a 2x cube, right? I will call this as equation 2 for time being. Let me continue it. Here you note that the area of the loop, the area of this particular loop, this is a circular loop, correct? Therefore, what is area of the loop? A is equal to pi A square is the radius of that. Now I want to solve for A square here. So A square is equal to A divided by pi. Now I am going to substitute this A square value in equation 2. Therefore, now equation 2 becomes mu naught n I A square is A divided by pi. I will write in the denominator A divided by pi, and remaining term as it is you write it x cube. We wrote it. But now we can identify what is this I into A is called. I into A is called magnetic dipole moment. Just we studied it, right? M is equal to I into A. Therefore, let me substitute it. That is equal to mu naught n. This is magnetic dipole moment divided by 2 pi x cube. I will just rearrange and write it. So I will write it like this: mu naught divided by 2 pi n into m divided by x cube. This is for n terms we took it. Now I will do one operation here. I will just multiply and divide it by 2. If I do that, what will happen? We will see. Multiply and divide by 2. Therefore, mu naught divided by, first I am dividing it. So 2 into 2, which is 4 pi. This becomes 2m divided by x cube. And you can take only for one turn. That's not at all a problem. So n is equal to 1 turn. Then you just observe this equation. Is this equation is looking like this particular equation? E is equal to 1 divided by 4 pi epsilon naught 2p divided by a cube, where we studied it. This is an expression for electric field along the axial line of electric dipole, correct? Where P is electric dipole moment and epsilon naught is permittivity of free space and E is the electric field, and A is the distance where we are finding the electric field. So this equation is exactly looking like this equation. Actually, this equation is for electric dipole moment, and this is an expression for, since it is similar to this equation, we are going to call the circular current loop. The circular current loop as similar to the magnetic dipole we can call this. Here m is equal to nia they called, or n is equal to 1 I took it, called magnetic dipole moment of the loop. This shows the current carrying circular loop is equivalent to the magnetic dipole.